like I said, we're going to stick with the same setup. We have our polyline and we have our geometric tolerance. And now, as I alluded to, what we want is we want the smallest subsequence of the vertices, still definitely from V1 to Vn, such that I have this condition about the replacements, the one that I also observed for Douglas Booker. So again, we are not actually optimizing under this condition, which is remarkably tricky. You'll see in the exercise sheet. We are optimizing under the condition that whenever I replace something with a straight line, the thing that I replace has Hausdorff distance minus epsilon to the thing. Unrolling the definition of Hausdorff distance again, we're kind of going to have the same thing that Douglas Booker was working on, which is to say, for every line segment and every vertex between those two vertices in the polyline, I have to have that this point has distance at most epsilon to the direct line segment. And now that we have it like this again, my question to you is, how would you model this? I'm selecting a subset of the vertices. I want to go from here to here. Think about it. And I already used a little bit of a suggestive word there. I used the word go. So I keep saying this, like we solve so many problems in this semester. We solve so many problems with graphs. So I'm going to turn this into a graph, and I'm going to look for paths in this graph. How can we set this up? I'll give you one more second to think about it, and then there it is. So the solution that Imai-Iri came up with in '88, or well, they published it in '88, so they probably came up with it a little bit earlier than that. The solution is I'm going to define a directed graph G equals VA with what they call allowed shortcuts. And what I'm going to do in this graph of shortcuts is find a shortest path from V1 to Vn. In this case, it's this one with only this single vertex, and this is going to be my answer. I want a graph that does this, but how do I get that graph and how is it defined? Think about that for a second. What this graph means is that the value of epsilon allows me to skip anything between. So, for example, I have all of my original edges. There isn't even anything to skip between those. So I can definitely have V1 followed by V2. That's fine. So that's an arc in my shortcut graph. And so the entire original polyline are arcs in my shortcut graph. And then, so for example, what I did in the Douglas Booker solution is I went from here to here. And I was allowed to do that because the straight line segment from here to here, if I look at all of the vertices between it, they had distance less than epsilon to the straight shortcut. So this, going from here to here, is an allowed shortcut in my shortcut graph, because if I somehow get to this vertex, I can then have Vn as the next vertex. So this Douglas Booker solution, which was a valid solution, is indeed a path in this graph. It goes from here to here to here, and then takes a shortcut, skipping this guy, straight to here. But as you can see here, which maybe wasn't super obvious before, but if we look at it, if we go from here to here, okay, this is a straight line, believe me, then actually this distance is also less than epsilon. So we hadn't really noticed before, and Douglas Booker definitely didn't notice it. Douglas Booker says, in relation to this thing that I wanted to do between V1 and Vn, this is the terrible node. We have to do something about that one, so let's go there. And then it turned out to also realize, then I also need this one. But if we now look at the entire thing, we actually see what you could do is rather than go here, you could go here and then get straight to the end. So that is the shortcut graph. I gave you the definition, but now the question is, how do we use this? And we're going to see a bunch of ways to do this, multiple ones anyway. But let's start simple. If I have the shortcut graph, then I can just do linear time shortest path calculation in this thing. Why is it linear time? Why don't I need Dijkstra? Well, we see this a lot in this lecture. It's a directed acyclic graph because every shortcut goes from a vertex to a later vertex. So this is an acyclic graph, and we can do shortest path in linear time. So that step is going to be fine. I can calculate the shortest path, but how do I get this graph? That's something that we're going to see multiple versions of. And the easiest thing to do is the following. For every vertex, I take that vertex as a node of my graph. And then for every pair of vertices where I less than j, and for every k between I and j, I test whether the distance between this point and the corresponding line segment is at most epsilon. So this is precisely the check of whether this is a shortcut edge or not. If this is true, then vi vj is a directed edge in my graph G. Otherwise, it isn't. I do this for everybody, and now I end up with a graph. And clearly, this is just straight up checking the definition for every possible edge. So this is definitely correct. This is the thing that I said I needed. But how much time does this take? Think about it for a second. Well, as you can see, I definitely have this for loop over pairs of vertices, and it's only in one direction, but that's still quadratic. And so this is already quadratically many times that I go through this loop. What do I do in the loop? Well, I loop over a third vertex, and you have to do the analysis a little bit more carefully if you haven't seen this before. But so how does this work out? It's ADS material. You can do your homework. But if you've done this before, like it's just nested for loops. So this ends up being 3 for loops deep, and we end up with cubic time. So order of n cubed. And order of n cubed is not cool. Geographic data are large. You saw this map of Europe that has thousands of vertices, and 1,000 squared is maybe okay, but 1,000 cubed is not cool. So we really should hope for something better than this. Just to still go into a little bit of detail of what the actual algorithm now looks like, is I have this cubic time algorithm to actually make the graph, and then I calculate the shortest path on the basis of dynamic programming. It looks a lot like the longest path from last video. I'm not going to go into details. This is a simple algorithm. We calculate the shortest path in linear time. Well, that's actually a little bit quick. I should be a little bit more careful there, because linear in what? Well, linear in the number of vertices plus the number of edges. I mean, if I have a lot of edges, then I need to look at all of them. So how many edges can the shortcut graph have? Think about it for a second. And if everything, for example, is on a single line, then all possible shortcuts are allowed. How many are there? It's between any vertex and any other vertex. So I have quadratically many edges in my shortcut graph. So I have to be a little bit careful there. Up until now, when we're working with polylines, the number of edges is always the same as the number of vertices, one fewer. But now, in using this model of the shortcut graph, I've ended up having quadratically many edges. And if we're going to have this shortcut graph, this is kind of necessary, because there can actually be n squared legit shortcuts. So we're kind of stuck with at least quadratic time in the number of vertices of the polyline. And this is the total runtime of the Imai-Iri algorithm. We make this graph in cubic time, then we find the shortest path in quadratic time, and so in total that's cubic time. And now the next question is, can we find this shortcut graph in less than cubic time? Like, it wouldn't really help us to do it faster than n squared, and we're not going to, but it would be nice if we could do it in n squared, because then that actually improves the actual runtime of the algorithm, and we're going to be able to do this improvement. So in general, this is something that you can think about. Like, if you have multiple steps in an algorithm, you have to think about, where can I actually do something? It doesn't help us to make this faster because the graph is that large. It definitely helps us to do something here because that actually improves the total runtime. But it wouldn't really help us to do this faster than n squared because we have this other step that we're definitely going to need to do. So with that said, let's look at the time it takes to generate the shortcut graph.